Hello friends, this is a bending load problem on the shaft. A shaft is subjected to a bending load of 3 kilonewton. So the sketch is given. This is the given sketch of shaft and the bending load is 3 kilonewton and the torque transmitted is 1000 newton meter and axial pull force of 15 kilonewton. Okay. The diameter of the shaft is 50 millimeter and length of the shaft is 250 millimeter. We have to calculate the stress at point A and B, stress at A and stress at B. So the given data is that bending load is W is equal to 3 kilonewton, that is 3000 newton. Torque is given, that is 1000 newton meter. In terms of millimeter you have to convert, and pulling force that is given 15 kilonewton, that is equal to 15,000 newtons, and the diameter and length. Fine. So initially we will calculate the tensile stress at point A and B due to axial pull. So the tensile stress sigma T is equal to F by A, and A is equal to pi by 4 into D square for shaft. So we'll get tensile stress sigma T as 7.64 newtons per millimeter square. And next is bending moment at A and B. So the bending moment M equal to W into L. W is the bending load that is acting at this point, 3 kilonewton into 250, so that is equal to 75 into 10 to the power 4 newton millimeters. Next, section modulus for the shaft. So this equation from table 1.3a design data handbook, K. Mahadevan and Balveer Reddy. The heading of the table is properties of various cross sections. In that image or sketch it is given, that is type G sketch. So this equation you will find section modulus for shaft, and D is given there, that is same as diameter. They have considered capital D, but we have considered small d, or else you can replace small d by capital D itself here. So substitute and we will get Z as 12,271.85 millimeter cube. And next step is bending stress at point A and B. So bending stress at point A and B, sigma B is equal to M by Z. So sigma B I have considered as a bending. So sigma B is equal to 61.12 Newton per millimeter square. Next step is according to the figure, bending stress is tensile at point A and compressive at point B. See here, bending stress is tensile at A and compressive at B. When this load is acting on this end, this will be pushed down. So A will be tensile and B will be compressive. So resultant tensile stress at point A, that is sigma A is equal to sigma B plus sigma T. Sigma B we have here, sigma T we have calculated here. Substitute. For tensile it is positive here, and for compressive stress this is negative, sigma B minus sigma T. We'll get sigma A and sigma B values. Next, shear stress at point A and B due to torque transmitted. So because of the torque transmission we have to calculate the shear stress. This equation we will use. This is the equation from shaft concept. So equation number 3.1, same data handbook. So we'll get tau is equal to 40.74 newtons per millimeter square. Next, principal stresses we have to calculate. We are asked to calculate the stresses. So the maximum principal stress at point A, that is sigma 1. In the data handbook the equation is sigma 1 is equal to sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 whole square plus tau xy square. It's equation 1.8c design data handbook. So here this is one dimension problem. See, only in the one dimension, so y term gets 0. This 0 it is considered as 0. So sigma y is 0. So sigma x, in the place of sigma x I'll substitute sigma a, because for a tensile stress at a I have considered a sigma a, that is why sigma a I have considered in the place of sigma x, and tau xy I'll consider just tau. Okay, just tau I'll consider, just because I have considered tau here, or else you can make this as tau xy if you want to keep it as it is. So next one a I have considered because there are point a and b here. So to differentiate values I have considered one a. For this calculation is particularly for a. So sigma 1 a is equal to sigma a plus square root of sigma a by 2 whole square plus tau square. So after that, see the substitution for sigma 1 a is equal to, we have value of sigma a, that is 68.76 divided by 2 plus 68.76 by 2 plus tau value 40.74. Okay. So we'll get sigma 1a as 87.69 newtons per millimeter square, that is tensile. So minimum principal stress at A, that is equation 1.8d. So same corrections I have made. So sigma A, for this is for A, point A, that's why now in the equation it is given as 2 for point A to A. So substitute similarly, but here the symbol is minus, earlier it was plus here. For maximum principal stress it was plus, and for minimum this is minus. Okay, and remaining everything is same. So we'll get sigma 2a in terms of negative sign. So this is compressive. Next, for point B, similarly you have to substitute for point B, in the place of A you have to substitute B. So you'll get sigma 1b and sigma 2b. Okay, so the next step is shear stress. Shear stress at point A, that is tau A is equal to plus or minus square root of sigma x minus sigma y by 2 whole square plus tau xy square. So 1.8 F, same data handbook, design data handbook, equation number 1.8 F. So sigma y is 0 anyhow. So sigma x, in the place of sigma x, sigma a have considered, and tau xy is tau square. Okay, so substitute these values similarly, and you will get tau a as 53.31 newtons per millimeter square, and tau b, for tau b you will get the value as 48.73.